Let's complete the proof of the theorem that we stated, which is that if you take the cyclotomic extension q of zeta of q, so recall what is zeta here. So I'm looking at the polynomial x to the n minus 1 and looking at its roots, and zeta here denotes the primitive nth root of unity e to the 2 pi I over n. Okay, and what we have shown from say the last two parts is the following, that the minimal irreducible polynomial, so the minimal polynomial of zeta over q, the irreducible polynomial that zeta satisfies is just the nth cyclotomic polynomial. So recall that we had the nth cyclotomic polynomial, which we said is just the product over all gamma primitive nth roots of unity x minus gamma, and this has degree of this polynomial, so degree of phi n of x is just the number of integers between 1 and n which are relatively prime to n. So that's what we call Euler's torsion function. And so now that proves this theorem, because q zeta over q, the degree of the extension, recall, so I have q and I adjoin a single element zeta to it, then the degree of this extension is just the degree of the minimal polynomial, right? So it's just the degree of phi n, which is phi n. Okay, so that completes the proof of the theorem. So recall now that as we said in the beginning, that this is actually a Galois extension. So this field here is what we call the nth cyclotomic extension. So this is called a cyclotomic field or a cyclotomic extension of q, and maybe we'll also say nth cyclotomic to keep track of the fact that it's nth roots of unity that you're adjoining. And we have already said that this is a Galois extension. Recall, q zeta over q is a Galois extension. Okay, it was normal because it's just the splitting field of the polynomial x to the n minus 1. It's separable because q has characteristic 0. Okay, so now given the fact that it is Galois, we want to understand its Galois group. Okay, in other words, what is the group of automorphisms of q zeta over q? Okay, so what is this? What is the Galois group? Okay, so we need to, well, we know something about it definitely. We know from, say, the fundamental theorem of Galois theory and so on, we know that the cardinality of the Galois group is just the degree of the extension, right? So this is just the degree of the extension, which is phi of n. Okay, so that's the Euler's torsion function of n. So what we will do next is to sort of construct explicitly these many elements, phi n number of elements in the Galois group. Okay, so what does a Galois group mean? Recall, we are looking therefore to construct automorphisms of the field q of zeta. Okay, so I'm going to try and construct some maps which I'll call psi sub k, such that when I restrict it to q, it gives me identity, right? It's the identity map on q. Okay, and what should psi k satisfy? Psi k should be an automorphism, should be a field automorphism of q zeta. So any field automorphism is automatically identity on q because it maps 1 to 1, therefore it automatically maps 2 to 2, 3 to 3 and so on. Then one can also show it maps p by q to p by q. Okay, so I'm going to construct such automorphisms, one for each element. So what is k here? K is going to run from 1 to n, and the GCD of k and n is 1. So for each such k, I'm going to construct. Okay, so that's what I'm going to do. We will construct such automorphisms. Okay, so how does one do this? Well, we already have the various ingredients required to construct such a map. So recall from what we have done before that when I have this extension q zeta, how do I construct an automorphism? Well, what I can do is I can map zeta. So an automorphism, recall, is uniquely identified once I know the following. So I know its identity on Q. In order to define an automorphism, what can I do? I have to say what zeta maps to, right? I must try and find a suitable candidate to map zeta to. Now recall from what we have said before that whatever zeta maps to has to be, so if it's some beta, then so under this automorphism psi, then beta, so if psi maps zeta to beta, then beta must also satisfy the same polynomial that zeta satisfies. Then we must have that this is 0. Okay, and also recall conversely, given any such beta which satisfies the same minimal polynomial as zeta, you can always define such an automorphism. Okay, so these are all facts that we have proved before. Conversely, given any beta, any root beta of the minimal polynomial, which in this case is phi sub n of zeta, there exists such an automorphism, okay, which maps mapping, should say there exists an automorphism mapping zeta to beta. Okay, now what does this tell us? So I just need to look for the other roots of the minimal polynomial phi sub n. And what are the other roots? We already know what they are, right? So phi sub n, the cyclotomic polynomial, is just the product of all the primitive nth roots of unity. Okay, so what are my various choices? So what do these look like? They are just, well, x minus if you wish zeta power k, the various powers of k which are relatively prime to n. Right? Those are the elements of gamma and star. So therefore, for each such k, I have therefore constructed an automorphism. So for each, by this general principle, for each k between 1 and n, GCD k with n is 1, there exists a unique, in fact, because once you specify what zeta goes to, the automorphism is uniquely defined. There exists a unique automorphism psi k. So just say there exists a unique psi k in the Galois group, which maps, well, it has to map q to q by identity, that's sort of forced, which maps zeta to zeta power k. Okay, so this is the description of psi k. Okay, now the point is, how many psi k's have we constructed? Well, we have constructed exactly phi of n, the Euler's torsion function of n, number of psi k's. Okay, so because we know that the Galois group, or this automorphism group, that's the Galois group, this is really G. Since we know that this has the correct cardinality, implies that this collection of psi k's that we have constructed this must be the entire group G. This must be the Galois group. Okay, now these automorphisms which map zeta to zeta power k. Okay, so what are these? They are actually, they are familiar. We sort of know what they are. Well, to understand what these automorphisms do, let's understand the group structure. So what's the composition law here? What happens when you compose two such automorphisms? Well, if I compose psi k1, psi k2, where k1 and k2 are both relatively prime to n, what does this give me? Well, let's see what it does to zeta. So this maps, so this is psi k1 on zeta power k2. Okay, now psi k1 is a homomorphism, it's a field homomorphism. So this is just, if I know what it does to zeta, then I just raise that to the power k2. So this is just xi to the k1, k2. Okay, so what is this? Well, therefore it means that the composition psi k1, psi k2 must be the same as psi of the product k1, k2, because they match on, because they take the same value on zeta, because both take the same value on zeta. Okay, and of course on q they are both necessarily the identity. Okay, so what law is this? Well, this looks exactly like the usual multiplication rule. So of course here I only have to look at the values of k which are relatively prime to n. So what exactly is this? Well, this is just the group. So let's take the group z mod, the cyclic group, if you wish, z mod nz star. Okay, what does this mean? This is just integers modulo n, but I'm just going to take the units in this ring. Okay, so this is, maybe let's just say it's all numbers. Well, one way of saying it is it's all numbers from 1 to n which are relatively prime to n, and this is thought of as a group under multiplication modulo n. Okay, another way of saying it is that this is just the group, well, this is isomorphic, if you wish, to the group gamma n star of primitive nth roots of unity under multiplication. So you should think of this primitive nth roots of unity as a group under multiplication. So they are all some complex numbers, and if you multiply two primitive nth roots of unity, what you get again is a primitive nth root of unity. Okay, so this is the group structure. So now it's an easy exercise from all that we have said. So observe that the Galois group, the group of automorphisms, is nothing but this group z mod nz star. Okay, so the group of units of this ring, if you wish. So this is just nothing but the group of units, if you wish to think in terms of the ring z mod nz. Okay, and the group of units means the invertible elements, and they are a group under multiplication. So this is under multiplication. Okay, and what is the isomorphism? Given any k here, we just map it to the corresponding psi sub k. Okay, and we have more or less shown the calculation we just did on the composition rule just says that the multiplication on the z mod nz level translates into the composition of maps psi k. Okay, good. So we exactly understand the cyclotomic extension and its Galois group. The corollary is that the Galois group is abelian. So observe the Galois group of the cyclotomic extension is actually an abelian group. Okay, it's just the group of units of this ring, this commutative ring. Okay, now what does this have to do with a problem that we considered earlier? So this is ruler and compass construction. So let me say R and C, ruler and compass, constructibility of the regular n-gun. Okay, so the problem is as follows. We know the regular polygons. Now can you construct using ruler and compass the regular polygon with n sides? Okay, so what's a regular n-gun? Well, its vertices you can think of as being, well, they form equal angles, 2 pi by n, 4 pi by n, and so on. So this angle here is 2 pi by n, and so this is, I mean, if you think of this as the unit circle in the complex plane, these vertices are exactly the roots of unity. Okay, but we'll think of it on just the usual plane R2. So observe that to construct the regular n-gun, well, remember this point is assumed to be given, right? When you do ruler and compass constructions, you assume 0 and 1 are given. Now if you can construct this point here, then of course you can construct the regular n-gun, okay, because you can draw the unit circle, and if you can construct this first point, then I can construct all the other points as follows. I just keep my compass here, I measure this distance, and now I put the center of my compass at the next point, and then I cut out the same distance here. So that will give me the next vertex. Again, I measure the same distance, and so on. Okay, so once you know what the correct distance is of a side of a regular n-gun, you can just measure that everywhere and construct the full regular n-gun. Okay, so the first observation is that a regular n-gun is constructible. Regular n-gun is constructible if and only if this angle 2 pi by n, the angle 2 pi by n is constructible. Okay, you can construct that angle somehow using ruler and compass. And recall again, we've looked at this before, constructing an angle is the same as sort of constructing this point here on the unit circle, and that point has coordinates cos and sine of 2 pi by n. So this is the same as saying cos of 2 pi by n is a constructible real number. Okay, so we have seen this before already. Now, I mean, if cos can be constructed, then sine can also be constructed. Okay, because once you know cos, you sort of draw a right triangle and so on. Now, the point is, let's prove the following theorem. So remember, what is this cosine here? So what has this got to do with the whole analysis of cyclotomic extensions that we have been doing? So observe the following. So maybe I'll just write the theorem down first. Proposition that cosine of 2 pi by n is constructible, or in other words, a regular n-gun is constructible. If and only if phi of n, the Euler's torsion function, is a power of 2. Okay, so let's prove this proposition. Proof. So first, let's call this number something alpha, which is cosine of 2 pi by n. This is just zeta plus zeta inverse by 2. Okay, what is zeta? Zeta is our complex nth root of unity, and if you just compute this plus minus of this, I mean e to the minus 2 pi I n by 2, that's, well, one of the definitions of cosine. So alpha is just zeta plus zeta inverse by 2. So what that means is that, so if we just simplify, that's just zeta plus 1 by zeta is 2 alpha. In other words, zeta square minus 2 alpha zeta plus 1 is 0. Okay. In other words, if you think of q, and if you look at the cyclotomic extension q zeta, and you look at q of alpha here. So observe, alpha is zeta plus zeta inverse by 2, means of course that alpha belongs to q zeta, right? This is certainly an element which is in the field q zeta, because if zeta is there, zeta inverse is there. So it's sort of an intermediate field. Q alpha is between q and q zeta, and this equation here says that zeta square, so zeta satisfies this quadratic equation, this quadratic polynomial. So what quadratic polynomial? Let's call it f. F of x is x square minus 2 alpha x plus 1. Okay, it's a root of this quadratic polynomial. Sorry, zeta is a root of this quadratic polynomial, and this quadratic polynomial has coefficients in q alpha. Okay, so what that means is that zeta, q zeta, if you think of it as an extension of q alpha, so this extension here, it has degree at most 2, because zeta is just, I mean, I can think of this as first you adjoin alpha, and then you adjoin zeta to it. Okay, so this additional adjunction of zeta, the zeta satisfies only a quadratic polynomial, so this can be at most degree 2, but it's in fact exactly degree 2. Okay, why is it 2? Observe that q of alpha is actually a subset of the real numbers. Okay, alpha is after all a real number. So Q alpha is purely real, whereas zeta is not real, right? So if n is at least 3, so let me assume here that n is at least 3, because I'm trying to construct a polygon, so n must be at least 3 for it to be a polygon. So since n is at least 3, then this element zeta is definitely not a real number. Okay, so that implies that zeta can't live inside, which implies zeta can't be an element of Q alpha. So what we have just said implies that Q zeta, this field over this field Q alpha, has to have degree exactly 2. Okay, so what we know now is that this is a degree 2 extension. Okay, and this is the cyclotomic field over Q, and that we know is a degree phi n extension. Okay, now let's look at what that implies. Well, that says in particular that Q alpha over Q is of degree phi n by 2. Okay, so that's the conclusion we wanted. So if I look at the extension Q alpha over Q, its degree is phi n by 2. Okay, now recall constructibility of a real number. When is it possible to construct a real number? So we have seen all this. Recall, alpha is constructible. So alpha is a real number, is constructible if and only if it belongs to a tower of extensions. So there exists a tower of extensions. So let me call this K0 contained in K1 contained in some KR. Okay, as a tower such that, well, this bottom tower is just Q is this, and this top tower, this is a tower such that alpha belongs to the last element of the tower, and each extension is of degree 2. Okay, ki minus 1 is a quadratic extension for all I greater than or equal to 1. Okay, so you can get it inside a tower of successive quadratic extensions. So this was the theorem on constructibility. So in particular this means, so what does it mean? In particular this means that K0, which is Q, it's just a product of the degrees of the intermediate extensions. So this is just 2 power r in this case. Okay, so it's a power of 2. Okay, so what does that mean? Therefore alpha is constructible implies that the degree of this extension, in particular it means that alpha belongs to some kr. So it belongs to some kr which is an extension of Q such that krq is some power of 2. So here's the setting, kr is here, q is here, alpha belongs to kr. So I can look at, so alpha is an element here, so I can just look at q alpha. Okay, I just adjoin alpha to q and look at this whole thing. What I know is that this overall guy is some power of 2, right? This has degree which is a power of 2. So these intermediate extensions must have degree which divides this overall degree, which implies that q alpha q divides this degree 2 power r, which implies it's also a power of 2. Okay, so q alpha q is therefore a power of 2. Okay, and we have already said q alpha q is just phi n by 2. So this is a power of 2, means that phi n is a power of 2. Okay, that's exactly what we wanted to prove. Phi n is a power of 2. Okay, so one direction is proved. So let's prove the converse. So let's go back. What did we want to prove? Cosine is constructible if and only phi n is a power of 2. So we have shown one way implication. Now let's do the converse. If phi n is a power of 2, okay, so converse. Okay, so if phi n is a power of 2, then so is, well, let's look at, okay, so phi n by 2 is also a power of 2, of course. So let's think in terms of the fields. So I have the cyclotomic extension q zeta over q. This is some power of 2, and what I have in the middle is this extension q alpha over q. Okay, so they're all powers of 2. All the extensions involved, we have assumed they are powers of 2. Okay, so this is some power of 2, so 2 to the something. Therefore, each of these must also divide it, must also be of the form 2 power something or 2 power something. Okay, now what else did we know? We know that this is a Galois extension. So what is a Galois extension? Q zeta over q is a Galois extension. But we actually know something more with abelian Galois group. Okay, we already proved this. It's just the group of units of the ring Z mod nz. So it's got an abelian Galois group G. Okay, now let's use this fundamental theorem of Galois theory. What does it say? It says that intermediate subfields, for example this one, are in one-to-one correspondence with subgroups of G. Okay, so in this case q alpha is some intermediate subfield, so that will correspond to some subgroup. So let's call that H. Let H denote the subgroup corresponding to, so I'm using the fundamental theorem of Galois theory here. So let H denote the subgroup automorphisms of q zeta over q alpha. Right, that was the association, the fundamental theorem. So we know that this is a one-to-one correspondence. Now what do we know here? We know the following: this is an abelian Galois group, right? G is abelian, H is a subgroup, which automatically implies it is a normal subgroup. Okay, because G is abelian. And what does that give us? It tells us, so recall the second part of the fundamental theorem. It says if your subgroup is normal, then in fact the subfield that it corresponds to, which in this case is q alpha, is Galois over the base field. Okay, so this therefore implies, I'm using the sort of follow up to the fundamental theorem, which says that if H is normal, then the subfield that it corresponds to, which in this case was q alpha over q, is Galois. Okay, and what's the Galois group? Well, it's just G mod H, right? With Galois group G isomorphic to G mod H. Okay, so maybe we'll call this something G tilde. This is the Galois group of q alpha over q. Okay, good. So now we are in good shape. We can now forget about the cyclotomic extension. Now we really only wanted to get something about q alpha over q. We have concluded it's a Galois extension. Its Galois group is an abelian group. So G tilde is also abelian. So this is Galois. It's got an abelian Galois group. And further, the Galois group has cardinality, which is a power of 2. Cardinality of G tilde is phi n by 2. So that's also some power of 2. Okay, so this is 2 power r for some r. So this is what we know. Okay, and Galois group, cardinality is a power of 2. Now what is it that we need to prove? We need to show that alpha is constructible. In other words, I can realize alpha inside an extension which is obtained from Q by a sequence of by a successive tower of quadratic extensions. Okay, so I want to be able to find an intermediate tower like this. So recall, this is what we want to show, that alpha is constructible. What does that mean? I should be able to do the following: between q alpha and q, I should be able to put a bunch of subfields. Okay, so that this is the last fellow. Let's call it KR. I.e., want a tower like this with each successive extension of degree 2. Now, how are we going to construct a tower? Well, we use the fundamental theorem of Galois theory again. right? I know that this is a Galois extension. I know a lot about its Galois group, Galois extension with Galois group which is abelian and whose cardinality is a power of 2. How do I get a tower of extensions? Well, I look instead for a tower of subgroups, okay, and such that the successive quotients, or the cardinalities of the subgroups, the successive quotients of the cardinalities is just 2, okay. So we'll instead look at the level of, let's look at the Galois group instead of subfields. Instead consider the Galois group G tilde, which is Q alpha over Q. Now what do we know about this? And we'll produce a tower of subgroups if you wish, or a chain of subgroups. Okay. Now how are we going to do this? Well, recall that cardinality of G is some power of 2. Okay. Now what does that imply? Well, it's also abelian if you wish. Okay. But if you have a group which is a P group which is just 2 power r, if you wish, say by using sort of the stronger form of Sylow's theorem, for example. So what does Sylow's theorem tell you? Well, there is a Sylow subgroup. In this case, the group itself is 2 power r, so the Sylow subgroup is just the whole group itself. But there is also a strengthened version of Sylow's theorem which says that you also have subgroups of every order of the form 2 power k, where k is any number from 0 to r. Okay, so you could use that, or if you wish, you could use the fact that this is abelian and then use the fundamental theorem of finite abelian groups. So there's 2 different ways of concluding this. So let me just say, for example, the stronger form of Sylow's theorem says that there exist subgroups in fact there's a chain of subgroups, so there exist subgroups of the following form: H0 contained in H1 contained in H2 and so on, HR, such that the cardinality of, so this is the final group G tilde, the cardinality of each HI is just 2 power I. Okay. Now once you have this, then you are done, because from a tower of subfields, from a chain of subgroups, you just have to construct the corresponding tower of subfields by taking the fixed fields. Okay. So now define, maybe I'll call them L sub I to be the field corresponding to H sub I. So what is this? This is just, so this is the top field here. So maybe that's Q alpha. So I just take this to be the fixed field of H sub I. Okay, by which I mean I have take Q of alpha, the top field, and then look at the elements which are fixed by HI. Okay, now what would you get? You would just get something which goes in the opposite direction. So in other words, I have G tilde here and I have identity at the other end. So this is H0 contained in H1 contained in blah blah blah. This is HR. Right, now at the level of fields, it just goes in the other order. So LR, which is the fixed field of HR, would be, well, that would just be Q, because that's the Galois group, right? HR is the whole Galois group, and then L0 would just be the whole, because it's the identity, is the whole field, and now these go in the other order. Okay, L1 is a sub of L0, is a sub of L2, and so on. Okay, so in any case, the numbering is sort of the opposite, if you wish, but the key point here is that if you look at the degrees of these extensions, Li plus 1, observe this again by the fundamental theorem of Galois theory, if you wish, is, so Li corresponds to which subgroup? Li corresponds to the subgroup Hi. So I'll have an Li somewhere Li plus 1 comes after it. So Li corresponds to some hi, Li plus 1 corresponds to hi plus 1, so it goes in the opposite order. This is just the cardinality of hi plus 1 divided by cardinality of hi. Okay, this is just from the fundamental theorem again. Okay, and now the way we have chosen it, this is just 2. Okay, so that completes the proof. So that says that you can actually construct such a tower of successive quadratics, which finally alpha belongs to the topmost guy in the tower. Okay, so this completes the proof. This implies that alpha is constructible. Okay, now finally, to complete this whole analysis, so sort of an aside, or finally, is it possible at all that when is phi n a power of 2? That's a question that one wants to understand. Now, can it even be a power of 2, right? Now, well, what's phi n? There is a simple formula for phi n. So if you write n as a product of primes, so n looks like, say, 2 power a, 3 power, let's give these names. This is n, okay. 2 power n, sorry, let's call it m2, or maybe a2. 2 power a2, 3 power a3, 5 power a5, and so on. So take all primes, p power ap, right? N has some prime factorization, so I just call the exponents as aps. They're all non-negative integers. Now phi of n is, let me use this little fact about phi of n. It is, I just have to take, you know, it's a product of all these phi of each of them, and in each case it is 2 to the a2 minus 1 into 2 minus 1, okay, then 3 to the a3 minus 1, 3 minus 1, and so on. So in general, p to the ap minus 1 to p minus 1. Okay, so this is only for the APs which actually occur in the decomposition. Okay, so I shouldn't write this for all numbers. So let me assume that I only write those prime factors which actually occur in the decomposition. Okay, if it's 0, then I don't want to write that then. Okay, so this is the product only corresponding to the terms which occur. Okay, now the point is, when can this possibly be a power of 2? So I want this to just be a power of 2. So that's a very restrictive condition, right? Because you see, this number here is clearly not a power of 2. This is not a power of 2. So unless somehow this power here becomes 1. Okay, so if these powers become 0. So if this is a power of 2, then when is that possible? Well, this implies that all these higher powers, so AP has to be 1 for all primes P which occur, which are not 2, for all prime, for P not equal to 2. Okay, for all prime factors P of n, for all, write it like this, for all prime factors P of n other than 2. Okay, only then these powers will all vanish. Okay. And further, what more do you want? And you need something more, that if a prime P occurs, if P, okay, occurs as a prime factor, P greater than 2 occurs as a prime factor, then what more do you want? You also want P minus 1 to be a power of 2. This should be a power of 2. Okay, because that's the other term which occurs in the formula for phi n. Okay, so that's already very, very restrictive. So what does this mean? So we have concluded, and observe, this is if and only if. So if these conditions all hold, then definitely phi n is a power of 2, because we have taken care of both the kinds of terms which can appear. So what does this mean? This says that phi n is a power of 2. Is a power of 2 means is the same as saying n looks like the following: n is some power of 2, doesn't matter which power, times some product of prime powers, the other primes. Okay. Now the other primes which occur must all occur with AP equal to 1. Okay. So each of the other primes which occurs with coefficient 1. So let me just say there are other primes P1, P2, P3, Pk, where what are the Pi's? Pi's are greater than 2, they are primes, they are all distinct, and they are very special primes. Okay, they are primes which have the following property, that Pi minus 1 is also a power of 2. Okay, so these are a very special type of prime, and this has a name. This is called a Fermat prime. A Fermat prime P, a prime P is called a Fermat prime if P is of the form some power of 2 plus 1. Okay, so Fermat prime P is a Fermat prime if P is of the form some power of 2 plus 1 for some k. Okay, and it's in fact not too hard to see that if some power of 2 plus 1 is a prime, then in fact it implies that k itself must be some power of 2. So this is again k must be a power of 2. Okay, this is sort of a simple exercise. You can show that if k is not of this form, then P can't be prime. You can find a common factor. If there is some odd factor, if k has an odd number dividing it, then you can easily pull out a divisor of P. Okay, so exercise, show that k must look like 2 power n. So in fact a Fermat prime is something of the following form. It's 2 to the L plus 1 for some L, and P is prime. Okay, so what we have finally shown is this very classic result whose special case. So example is, so finally to conclude, what did we say? We said that the regular n-gon is constructible. So finally we have shown that the regular n-gon is constructible if and only if the following happens: n looks like a power of 2 power something multiplied by a product of distinct Fermat primes. Okay, now, and Pi is not equal to Pj or I not equal to j. Now what is an example of a Fermat prime? Well, 17 is sort of the classic example. Observe, this is just 2 power 4, just 2 to the 2 square plus 1. That's a Fermat prime. Okay, and this is sort of the famous result due to Gauss, who discovered that the 17 sided polygon was actually constructible using ruler and compass. Okay, and here's a more general result on constructibility of regular n-gons.